Am I audible? Am I audible?
Audible, sir.
Okay.
Yes, sir.
Sir.
Okay.
Yes, sir, yes.
Okay. Thank you. So, for your for exam, let us have this class. You can have your doubts in course of the discussion, and we'll have it in a doubt clearing mode. So there are differential equations you can encounter in physics, engineering, and other branches of science. So you might have come across differential equations and partial differential equations. And partial differential equation can be a linear partial differential equation or nonlinear partial differential equation. Apart from Laplace equation and Poisson equation, you can have your uh, heat diffusion, wave equations, Fredholm, Volterra equation, telegraph equation, Klein-Gordon equation, Schrodinger equation, Dirac equation. These all are having partial differential equation in it. So, the basic concept of solving partial differential equation, let us discuss. Sorry for this one.
Screen is not visible.
Am I visible?
Yes, sir.
So due to power cut, disturbance or else could not connect. No. So, we are discussing some of the green properties for programs that includes equation, Laplace equation, Poisson's equation, rate differential equation, integral equation, variable equation, integral equation, Schrodinger equation, static equation. So, we can consider partial differential into in the basis of their order. Regularly. How partial differential equation more commonly used? Second, in an equation, in a differential equation, you have some variables and some
Your voice is not clear, sir.
constants.
Hello,
Is
sir.
it audible now? Is it audible now?
Hello.
Is it
Yes, sir.
audible
Your
now?
voice is not clear. Please check your internet connectivity, sir.
Is it audible now?
Now it is audible.
Okay, so there may
Yes.
be some internet problem. So we are discussing partial differential equation and its solution. So partial differential equation, to solve the partial differential equation, one of the most commonly used method is
Sir, your
separation.
voice is not audible clearly or properly.
Okay, so what can I do? So let us disconnect and connect again. Am I audible? Am I audible?
Okay. Okay,
Yes,
okay,
sir.
sir.
Now,
Oh,
yes.
Yes, sir.
okay, okay. So a differential equation may be in the form n, which is a function of y dy, is equal to m, which is a function of x dx. If it is not in this form, that is, so usually the coefficient of dy should contain the terms of y only, and the coefficient of dx must contain that of x only. Am I audible? Am I audible?
Yes, sir.
No, sir.
Yes, sir.
No, sir.
Okay. So if it is not in this form, that means if you have something mx py dx is equal to ny qx dy, then the coefficient of dx is a mixture of terms containing x and y, and the coefficient of dy is a mixture of terms containing y and x. Then you have to separate the
Sir,
variables
voice
in
is
both the sides.
audible, but the
So what
volume
you
is
can
too
do,
less, sir.
you can
Hello, sir.
rearrange the terms as mx by qx dx is equal to ny py dy. So this method is called separation of variable. Now you can see here in your text, suppose f is a function of x and t, where x is capital X is a function of small x and capital T is a function of small t. Let us have, for simplicity, you have f is equal to x sin omega t. So what you will do? So you can separate the variables in both the sides, and you have your del f by del x is equal to x dash t, and del square f by del x square is equal to x double dash t. So your del f by del t is equal to x t dot, and del square f by del t square is equal to x t double dot. So in wave equation, your d square f by dt square is equal to v square d square f by dx square. So this can be solved by separation of variable, and you have your solution t double dot, which is a function of small t, minus k v square t, which is a function of small t,
is equal to 0. So by assuming a separable solution, we have reduced a partial differential equation in two variables into two equivalent ordinary differential equations. Okay? Any doubt? So you can see here that your t terms are are brought into one side of the equation here. You can see here x t double dot is equal to v square x double dash t. So by dividing throughout v square x t v square x t, you can get t double dash by v square t is equal to x double dash by x. Are you getting it? So this can be solved by t double dot by v square t is equal to k, which is a constant which is equal to x double dash by x. So by solving this, you can have your expression x double dash minus kx is equal to 0 and t double dot minus k v square t is equal to 0. So the ordinary differential equation can also solved by using this technique also. So there are some examples. So you can also solve Laplace equation by separation of variables in Cartesian coordinate system like this: del square f by del x square plus del square f by del y square plus del square f by del z square is equal to 0, where f is a function of x, y and z. So your del f by del x is equal to x dash y z, del square f by del x square is equal to x double dash y z, and del f by del y is equal to x y dash z. So your del square f by del y square is equal to x y dash y double dash z, del f by del z is equal to x y z dash z double dash, and del square f by del z square is equal to x y z double dash. So by substituting, you can have x double dash by x plus y double dash by y plus z double dash by z is equal to 0. So it is the second derivative, del square x by del x square, del square y by del y square, del square z by del z square, which is written in double dash. So your x double dash by x is equal to 1 by x del square x by del x square is equal to minus k1 square. Similarly, y double dash by y is equal to 1 by y d square y by dy square is equal to minus k2 square, and z double dash by z is equal to 1 by z d square z by d small z square is equal to k3 square. So your minus k1 square minus k2 square plus k3 square is equal to 0. So Laplace equation can be solved, and you have x is equal to a cos k1x plus b sin k1x. Or similarly, your y, capital Y is equal to c cos k2y plus d sin k2y, and your z is equal to p cos hyperbolic k3z plus q sin hyperbolic k3z, and your k1 square plus k2 square is equal to k3 square. So the values of constants a, b, c, d, p, q are determined by the boundary conditions and initial conditions that apply in any given physical problem. The general solution of the Laplace equation is obtained by taking a linear combination of all possible product of the solution. Okay. So you can have your rectangular metal plate, which can be solved by separation of variables. Similarly, you can solve Laplace equation in cylindrical coordinates. You know, in cylindrical coordinates, the function can be resolved into three components, that is rho cap, phi cap and z cap. So your rho, phi and z, f is a function of rho, phi and z. So your Laplace equation del square f is equal to 0. So this can be written as del square f by del rho square plus 1 by rho del f by del rho plus 1 by rho square del square f by del phi square plus del square f by del z square is equal to 0. So you can solve this by separation of variable. So this is one of the problem which you may try. Consider a solid cylindrical cooling tower of radius T2 unit and height 4 unit. Its base and the curved side are held at 0 degree and top at a constant temperature T0. So the steady state temperature distribution is described by Laplace equation del square T is equal to 0. So by specifying the boundary condition, you can determine steady state temperature distribution in the cooling tower. Then you can solve Laplace equation in spherical polar coordinates by separation of variable. Where your variables are r, theta and phi, and this the function f can be resolved into the components r cap, theta cap and phi cap. So Laplace equation del square f is equal to 0 can be written in spherical polar coordinates as 1 by r square del by del r square del by del r plus 1 by r square sin theta del by del theta sin theta del f by del theta plus 1 by r square sin square theta del square f by del phi square is equal to 0. So by separation of variables, you can write f is a function of r, theta and phi, capital R, capital theta and capital phi. Where capital R is a function of r only, capital theta is a function of theta only, and capital phi is a function of phi only. So you can have the equations like this: d square phi by d small phi square plus m square phi is equal to 0, r square d square r by dr square plus 2r dr by d small r minus n square r is equal to 0, and your theta equation will be d square theta by d square theta d theta small theta square plus cos theta by sin theta d theta by d small theta plus n square minus m square by sin square theta capital theta is equal to 0. So you can have your solution by separation of variable, and your phi will be am exponential im phi is equal to bm cos phi plus cm sin phi. So you can also use Frobenius method to obtain the solution, which I shall discuss. Then you can see that many important equations can be solved by separation of variables. And there are many partial differential equations in physics. One is Poisson equation, which can be written as d square f is equal to u, del square f is equal to u, where del can be expressed in Cartesian, cylindrical and plane and spherical coordinate system. So Poisson equation can be solved by separation of variable. Then heat diffusion equation, del square u is equal to 1 by k del u by del t. This can be also solved by separation of variable in a Cartesian coordinate system x, y, z, and it is also t dependent. Similarly, your wave equation, that is del square u by del x square is equal to 1 by v square del square u by del t square, can be solved by using separation of variable. Integral equation like Fredholm and Volterra equation can be solved by separation of variable. And you might have come across this type of solution in your BSc classes. But the most important thing is, some equations cannot be solved by separation of variable method only. This is a new type of equation, and you use power series solution or Frobenius method solution to solve those equations. So initially we have discussed some differential equations which can be solved by separation of variable, where let us reconnect.
in a differential equation, you might have constant coefficients or variable coefficients. Am I audible?
Yes, sir, audible.
Yes, sir.
So when there is constant coefficients like those I have discussed earlier in this class, there might have been differential equation having variable coefficients, and many differential equations with variable coefficients encountered in physics and engineering, and those cannot be solved by separation of variable method only, which is a general method. To name a few, we have Legendre differential equation, Bessel's differential equation, Hormey differential equation, Laguerre differential equation, associated Legendre differential equation, so on and so forth. You can see in Legendre differential equation in the Legendre differential equation, which is shown in the screen, you have 1 minus x square y double dash minus 2x y dash plus L into L plus 1 y is equal to 0. So you can see d square y, del square y by del t square or del x square. The general form of Legendre differential equation is 1 minus x square y double dash minus 2xy dash plus L into L plus 1 y is equal to 0. Okay. So you can see the coefficient of y double dash is equal to 1 minus x square, which is not a constant coefficient. X is a variable, so 1 minus x square is variable. So your coefficient of y double dash is a variable, 1 minus x square. Similarly, coefficient of y dash is also variable, minus 2x. Okay. Similarly, your y double dash is equal to del square y by del x square. Y dash is equal to del y by del x. So your 1 minus x square y double dash or del square y by del x square I think the screen is visible. So let us have these differential equations. Legendre differential equation. 1 minus x square y double dash. 1 minus x square y double dash minus 2xy dash plus L into L plus 1 y is equal to 0. So here the coefficient of y double dash is equal to 1 minus x square, which is a variable. Coefficient of y dash is equal to minus 2y, which is a variable. So Legendre differential equation is a differential equation with variable coefficients. So we need some special technique to solve this. Please mute yourself. Please mute yourself. Please mute yourself. Or the admin, mute. There is disturbance, please mute. Please, one of the participants has unmuted.
ଆଜି ମନେ ପଡିଗଲା ହଉ ଏଇନା କରୁନୁ ଦେଖିବି ଆଜି ବି ତ ମୁଣ୍ଡ କୁଣ୍ଡେଇନି ପୁଣି କେମିତି ଚୁଟି ଠିଆ ହେଇଛି ରେଜର ମାରିଦବା ଭଲ ହବ ଜଲ୍ଦି କାଟ ଯଥା ଶୀଘ୍ର ପାରୁଛୁ କାଟ କାଇଁ କଣ କରୁଛୁ ବେ ତୁ ମନ୍ତ୍ରୀଙ୍କ ଭଳିଆ ଛାଡ ହଉଛି ଟାଇମ ହଉନି।
Suchimita madam, please mute yourself. Mute yourself, Suchimita madam.
Okay. So Legendre differential equation is having variable coefficients. Similarly, your Bessel differential equation has the general form x square del square y by del x square plus x del y by del x plus x square minus k square y is equal to 0. So you can see the coefficient of del square y by del x square is x square, which is variable. Similarly, the coefficient of del square y by del x in Bessel's differential equation is x, which is a variable. And the coefficient of y is equal to x square minus k square, which is also a variable. So this is differential equation having variable coefficient. Similarly, in your Hermite differential equation, and the coefficient of y dash is equal to minus 2x, which is variable. And the general form Hermite differential equation is y double dash minus 2xy dash plus 2 alpha y is equal to 0. Similarly, the Lagrange differential equation is having a form xy double dash plus 1 minus xy dash plus y alpha y is equal to 0. So your x del square by del x square plus 1 minus x del y by del x plus alpha y is equal to 0. So you can see the coefficient of y double dash is equal to x, which is a variable. The coefficient of y dash is equal to 1 minus x, which is also a variable. So this is a differential equation having variable coefficients. So you can use power series method to solve this type of differential equations. So so the sum of an infinite number of terms of the form a0 plus a1 x minus x0 plus a2 x minus x0 square plus so on and so forth is equal to summation n is equal to 0 to infinite an x minus x0 to the power n is called a power series in x minus x0. So if you represent it in a Cartesian coordinate system, then your x0 is at the origin of the Cartesian coordinate system and x is any point in that space. So the coefficient an and the center x0 of the series are constants independent of the variable x. If the center of the series is x0 is equal to 0, becomes a0 plus a1x plus a2x square plus so on and so forth is equal to summation n is equal to 0 to infinite an x to the power n. So you can shift the center to 0. If x0 is at a point 4, 5, 6, minus 6, minus 7 or anywhere else in the Cartesian coordinate system, you can shift the coordinate and make x0 is equal to 0. So if x0 is equal to 0, then equation 3.1 can be modified into equation 3.2 and is a term, is a function of x only. So this is a power series in x instead of x minus x0. So this can be done by shifting the origin of the coordinate system to as per our convenience, or by replacing x minus x0 by x. So the exponent of power series are non-negative integers. So you can have some power series and you can have some examples 1 plus x square plus x cube plus so on and so forth is equal to summation n is equal to 0 to infinite x to the power n. It is a power series. 1 plus x plus 2 factorial x square plus 3 factorial x cube plus so on and so forth is equal to summation n is equal to 0 to infinite n factorial x to the power n. This is also a power series. 1 plus x square by 2 factorial plus x cube by 3 factorial plus so on and so forth is equal to summation n is equal to 0 to infinite x to the power n by n factorial. This is also a power series. So any term of the series has a negative or fractional powers. Okay, like 1 by x plus 1 plus x square plus so on and so forth. X to the power 1 by 2 plus x to the power 3 by 2 plus x to the power 5 by 2 plus so on and so forth. So these are not power series. So when any of the power of a series is having minus negative value of having minus 1, minus 2, minus 7, minus 9, minus 11, like that, or having fractions like 1 by 2, 3 by 2, 5 by 2, 1 by 7, 7 by 8, 9 by 17. This is also not a power series. So a power series summation n is equal to 0 to infinite n x to the power n is said to converge at a point x on the interval I if the limit, that is the limit, capital N tends to infinite, summation n is equal to 0 to n x to the power n exists for all x in I. Otherwise, the series diverges at that point. So the sum summation n is equal to 0 to capital N x to the power n is called the nth partial sum of the series. So the series converges and the sum summation n is equal to 0 to infinite n x to the power n is equal to fx is defined on I, and the series summation n is equal to 0 to infinite n x to the power n is called a power series representation of the function f of x. So if the series converges, then there is a radius of convergence, you know. So for the power series having the form summation n is equal to 0 to infinite n x to the power n, there corresponds a real positive number capital R such that the series converges if modulus of x is smaller than capital R and diverges if modulus of x is greater than capital R. The number R is called the radius of convergence of the series. The value of x for which the series converges form an interval from minus R to R, and it is called the convergence interval. The power series may or may not converge at either of the endpoints of the interval. So at x is equal to minus R or x is equal to R, the series may or may not converge at the terminal point. If R is equal to 0, the series converges only for x is equal to 0 and diverges for all x is not equal to 0. An example is summation n is equal to 0 to infinite n factorial x to the power n. If 0 is smaller than R is smaller than infinite, the series converges if modulus of x is smaller than capital R and diverges if modulus of x is greater than capital R. Similarly, if R is equal to infinite, the series converges for all values of x. So summation n is equal to 0 to infinite x to the power n by n factorial is a power series of this type. So the radius of convergence may be 0, for which the series converges only at one point, that is R is equal to 0. The radius of convergence may be infinite, for which the series converges at all points in the vicinity of the origin, and the series may converges at a particular interval from 0 to infinite or 0 to some other value. The radius of convergence of a power series can be determined from the coefficients of the series by the formula R is equal to limit n tends to infinite an by n plus 1. So let us have an example. So suppose you have a series summation n is equal to 0 to infinite n plus 1, 3 to the power n, x to the power n. Then you have your R is equal to limit n tends to infinite n by n plus 1 as per the formula 3.3. So if you put n is equal to n, so you have your n plus 1 by 3 to the power n plus 3 to the power n plus 1 by n plus 2. So your limit n tends to infinite 3n plus 3 by n plus 2 is nothing but limit n tends to infinite 3 plus 3 by n by 1 plus 2 by n is equal to 3. So radius of convergence is 3. Okay. So you can see your an is equal to n plus 1 by 3 to the power n. So n plus 1 will be n plus 1 plus 1, that is n plus 2 by 3 to the power n plus 1. So by putting this in the general expression, that is limit n tends to infinite n by n plus 1 modulus, you can have your radius convergence as 3. Similarly, you can have the convergence for other series also. So what are the properties of power series? Term as differentiation and integration. If a power series, that is in general form n is equal to 0 to infinite n x to the power n converges for modulus of x is smaller than capital R, where capital R is greater than 0, then the sum f of x is equal to summation n is equal to 0 to infinite n x to the power n is continuous and has derivatives of all orders for modulus of x smaller than r. The series can be differentiated term-wise. That means f dash x is equal to integration n is equal to 1 to infinite n a n x to the power n minus 1. That is nothing but a1 plus 2a2x plus 3a 3x square plus so on. So similarly, f double dash x is equal to summation n is equal to 1 to infinite n into n minus 1 n x to the power n minus 2, which is equal to 2a2 plus 3 multiplied by 2a3x plus so on and so forth. So each of the series resulting from successive differentiation also converges for modulus of x is smaller than capital R. That is radius of convergence. The coefficients an of the series are related to fx and its derivatives by an is equal to nth power of fx by n factorial at x is equal to 0. The series can also be integrated term-wise if the limits of integration lie within the interval of convergence of the series. So integration 0 to x f of t dt is equal to summation n is equal to 0 to infinite n by n plus 1 x to the power n plus 1 also converges for modulus of x is smaller than capital R. Similarly, we can have term-wise addition and subtraction of a power series. If two infinite series summation n is equal to 0 to infinite a n x to the power n and summation n is equal to 0 to infinite b n x to the power n are positive radius of convergence and converge to the functions of fx and gx respectively, then the two series can be added or subtracted term-wise. So you can have your fx plus minus gx is equal to summation n is equal to 0 to infinite a n plus minus b n x to the power n. So these two power series can be added together term-wise. And this converges for all x lying in the interior of the interval of the convergence of each series. Then term-wise multiplication and division. So in the series, that is summation n is equal to 0 to infinite a n x to the power n and summation n is equal to 0 to infinite b n x to the power n. This can be multiplied term-wise, that is fx gx is equal to summation n is equal to 0 to infinite cn x to the power n, where cn is equal to a0 bn a1 bn minus 1 plus so on and so forth an b0. This can be written as summation k to n ak b n minus k, or this can be written as k is equal to 0 to infinite a n minus k bk. The product also converges for each x in the interior of the interval of convergence of each series. And the quotient fx by gx is equal to a0 plus a1x plus a2x square plus so on and so forth by b0 plus b1x plus b2x square plus so on and so forth is also a power series if your b0 is not equal to 0. So in some cases, the quotient f by g may not converge at some points where both the series fx and gx converge. So both sin x and cos x converge for all x. For sin x by cos x is equal to tan x converges only if modulus of x is smaller than pi by 2. If two series summation n is equal to 0 to infinite a n x to the power n and summation n is equal to 0 to infinite b n x to the power n converge to the same function for modulus of x is smaller than r, then they must have the same coefficients. That means your n is equal to 0 to infinite a n x to the power n is equal to summation n is equal to 0 to infinite b n x to the power n, and your a n is equal to b n for all n greater or equal to 0. This is called identity principle. If fx is equal to summation n is equal to 0 to infinite a n x to the power n is equal to 0 for modulus of x is smaller than capital R, then all the coefficients vanish identically. That means n is equal to 0 for all n greater or equal to 0. This is called vanishing of all coefficients. You can also shift the index of summation. With an infinite series n is equal to 0 to infinite n x to the power n, the index of summation can be shifted by a number k, which is a constant, by simultaneously increasing the summation index by k, that is n is equal to n plus k, and decreasing the starting point by k. For example, summation n is equal to 3 to infinite a n x to the power n minus 1 can be written as integral summation n is equal to 0 to infinite a n plus 3 x to the power n plus 2. Okay, so in the summation you have to decrease by 3, and in other part, in the terms, you have to increase by 3. So then you know analytic function. The function fx is analytic or regular at a point x0 if it can be expressed as a power series. F of x is equal to summation n is equal to 0 to infinite n x minus x0 to the power n with r is greater than 0. And this is popularly known as Taylor series of expansion with n is equal to 1 minus n factorial nth derivative of f is equal to x0. All polynomials and functions like e to the power x, sin x, and cos x are analytic everywhere. If two functions f and g are analytic at x is equal to x0, their sum f plus g and product f multiplied by g are also analytic at x is equal to x0. The quotient will be analytic only if g at 0 is not equal to 0. Okay. By this, you can discuss our power series, how to solve the equations by using the power series. So the general solution, power series solution about an ordinary point. You know ordinary point and singular point. So let us discuss power series solution of an ordinary point. Okay, if x is equal to 0 is an ordinary point of the differential equation del square y by del x square plus px del y by del x plus qxy is equal to 0, then there exists a pair of linearly independent power series solution of the form y1, which is a function of x, is equal to summation n is equal to 0 to infinite n x to the power n, and y2, which is a function of x, is equal to summation n is equal to 0 to infinite b n x to the power n. And the radius of convergence of each series is at least equal to the distance of the nearest singular point of the equation from x is equal to 0. We shall illustrate the power series method of solution in the next class. Thank you.
सर
Okay.
हेलो सर
हाँ बताइए.
सर कैन वी गेट दिस पीडीएफ
Yes, no doubt. I shall give you as soon as it is being completed.
ओके सर
So over to Dr. Naik.
Yes, sir.
Anybody any doubt you can ask before Dr. Naik joins. Any doubt or any question?
Sir,
Just wait. Dr. Vivekananda Naik will take his usual class. He is going to join your class.
Hello, am I audible?
Yes, sir. Now it's audible.
Okay. Okay, so okay. 1 minute, please. So today we discuss about cyclic coordinate and then Hamilton's principle. Okay. So first, okay. Is slide visible? Hello?
Yes, sir.
Okay.
Sir.
So last class we have discussed about Lagrange equation. Yeah? Any question? Hello? Any problem? Hello, am I audible?
Yes, sir.
Yes, sir.
Okay, okay. Yes, sir. So last class we have discussed about Lagrange's equation of motion and generalized coordinate. Okay. Today we discuss about Hamilton's principle and derivation of Lagrange equation from Hamilton's principle. Before we go to details about the Hamilton's principle, um, we'll discuss about cyclic coordinate and then Hamiltonian. Okay, first then we go for Hamilton's principle. Cyclic coordinate. We have already know that for a conservative system, Lagrangian is the difference between kinetic energy and potential energy. And potential energy for a conservative system is generally a function of position only means generalized coordinates only. And a kinetic energy is a function of velocity generally, it may contain coordinates. Okay. So if I take the derivative of Lagrangian with respect to velocity, then derivative with respect to v will be 0. It will only del t by del qj dot. Okay, but del t by del qj dot is nothing but pj, generalized momentum. If you see t is equal to half mv square or half m, let's say mj qj dot square. This is your t. Velocity square half mv square, m means velocity. Velocity here is qj dot, qj is coordinate. If this is t, what is the derivative with respect to qj? Qj dot. If t is this, then del t by del qj dot is equal to how much? Hello? Hello?
Yes, sir.
Del t by del qz is how much? If t is equal to half mj qj dot square and del t by del qz dot is equal to 2 cancel 2 qj dot. So 2 cancel mj qj dot. Mass into velocity. Mass into qj dot is velocity. So mass into velocity is what?
Yes. Absolutely, sir.
Momentum. Momentum. So it is nothing but pj. So del L by del Qj dot is equal to Pj. We have used this formula when we calculate Pj from Lagrangian. The formula del L by del Qj dot is equal to Pj. Okay. This is one of the formula we will use for solving problems. So Pj is commonly known as canonical momentum or conjugate momentum. This conjugate momentum is associated with the velocity by this equation. Pj is equal to del L by del Qj dot. Pj may not be mechanical momentum because Qj is not always general position coordinate, so Pj is always not mechanical momentum. Okay. Now, if the Lagrangian system does not contain a particular coordinate, then for that system del L by del Qk 0. If Lagrangian does not contain Qk, then its partial derivative with respect to equal 0, and such a coordinate is called cyclic or ignorable coordinate. We call it a cyclic or ignorable coordinate. Cyclic coordinate means that coordinate does not appear in the Lagrangian. But from Lagrange's equation motion, we have this d by dt del L by del Qj dot minus del L by del Qj 0. If one coordinate is cyclic, then del L by del Qj is cyclic. This is 0. So we got d by dt del L by del Qj dot is equal to 0. But del L by del Qj dot is Pj. So basically this is Pj. So dPj by dt is equal to 0. So what it means? Hello? If derivative of something is 0, then that function is
Constant.
Constant.
okay. So Pj is constant. So if Qj is cyclic, Pj is constant. So corresponding canonical momentum is a conserved quantity. For a cyclic coordinate, corresponding momentum is a conserved quantity. Okay. Thus, generalized momentum conjugate to a cyclic coordinate is conserved. Okay. So example, if time is cyclic, if time does not appear in the Lagrangian, then total energy of the system is conserved. Energy is a conserved quantity. If time is cyclic, time does not appear in the Lagrangian, that means time does not affect the motion. You know in plus 2 where we energy conservation see, we measure the energy at each point. Actually body is falling with time, but each point energy is same. That means energy, total energy is independent of time. With time it is falling, but total energy same at each point. That means total energy is independent of time. Okay. Or Lagrangian is E is equal to T plus V. Lagrangian is T minus V. So if Lagrangian is independent of time, then we call energy is a conserved quantity. Similarly, if some translational coordinate is cyclic, then corresponding linear momentum is conserved. If some coordinate, translational coordinate Qj is cyclic, then corresponding linear momentum is conserved. If motion in the, you can say translational motion or spatial motion, change in one direction. If it is a cyclic, does not appear, suppose one coordinate x does not appear in the Lagrangian, then px is a conserved quantity. Y does not appear, then py is a conserved quantity. Okay. Third thing is, if some rotational coordinate is cyclic, corresponding angular momentum is conserved. If theta is cyclic, p theta is a conserved quantity. Okay. Because if the system is spherically symmetric, then all the components of angular momentum are conserved. Spherically symmetry means rotational invariant. So it is independent of rotation. Spherically symmetry, Lagrangian does not contain any rotational coordinate. So obviously angular momentum is a conserved quantity. But if the system is symmetry of z axis, then only Lz is conserved. If z does not appear, only Lz is. Z means z component of angle, or you can say rotation along z axis or about z axis. Okay. Any doubt? Hello? Hello?
No, sir.
Okay.
No, sir.
Then conservation of energy, actually this, I'll give you. The general form of Lagrangian for a system is L is a function of Qj dot T. Now I want to take derivative with respect to time. dl by dt is equal to how much? Uh, like when you know f is a function of x, y, z, then df is equal to how much? You write if x is a function of x, y, z, then df is equal to how much? You write del f by del x into dx plus del f by del y into dy.
Plus del F by
Hello? Plus del f by del z into dz.
Vj.
Yes. Similarly, here Al is a function of Qj means all Q1 to Qf, Qj dot, Q1 dot to Qf dot and T. Then if you take a derivative, total time derivative dl by dt, then it will becomes summed over z del L by del Qj into dQj by dt. Del L by dt, suppose here df by dt, then it will be del F by del x into dx by dt, del F plus del F by del y into dy by dt, del F by del z into dy by dt. Okay. So, so dl by dt become, please someone is on mute. Hello? Parameswari,
Parmeshwara Nayak.
please mute yourself.
Yes, sir.
Mute. Any problem?
No.
Please mute yourself.
Yes.
Okay. So using this, we can write dl by dt is equal to this summed over j del L by del Qj dQj by dt plus del L by del Qj dot dQj dot by dt plus del L by dt dt by dt. Dt by dt 1, so only del L by del.
Parmeshwara Nayak, please mute yourself.
Yes.
Okay. But from Lagrange's equation, we have this formula d by dt del L by del Qj dot minus del L by del Qj is equal to 0. So if I take to the right hand side, this will d by dt del L by del Qj dot is equal to del L by del Qj. Okay. Where del L by del Qj, I can put this d by dt del L by del Qj dot. So my equation becomes this dl by dt is equal to sum root j d by dt del L by del Qj dot plus this. But see, the derivative of this quantity into Qj dot plus derivative of A into B plus A into derivative of B. So finally, the derivative of A into B. Derivative of A into B is equal to derivative of A into B plus A into derivative of B. That's the formula. So I can write this sum over J del L by del Qj dot into Qj dot plus del L by del T. So if I take to one side, I can write this will be minus this quantity del L by del Qj dot is Pj. I have already derived this. Pj is equal to del L by del Qj dot. Okay. So putting that, I found Pj Qj dot, and I take this del L by del T to right hand side. So minus L dl by dt or minus L. This 0 I interchange nothing. Plus del L by del T is equal to 0. I have a equation like this. Okay? Hello? All are getting my
Yes, sir.
point or not?
Yes, sir.
Okay.
Yes, sir.
So we got this equation. If Lagrangian, but for conservative system, we know that Lagrangian does not contain time explicitly. Time is cyclic. We know for a conservative system, Lagrangian does not contain time. So energy is conserved. We call it a conservative system. So for a conservative system, Lagrangian does not contain time. So that quantity is 0. So for a conservative system, we have d by dt. This function is equal to 0. and that function is known as Hamiltonian H. So H is nothing but summed over J Pj Qj dot minus L. This J varies from 1 to F. I mean number of degree of freedom. Okay. So this quantity is known as Hamiltonian. If Lagrangian is given, we can calculate Hamiltonian by this formula. And but Hamiltonian is a function of Qj Pj T. Lagrangian is Qj Qj dot T. So we must replace all Qj dot by P when we write Hamiltonian. We will see in two problems. So the formula, so Hamiltonian can be calculated from Lagrangian by using this formula. H is equal to sum over Qj Qj dot minus L. Okay. ଜାଣନ୍ତୁ କାଲି ଟିକେ ବେଳାରେ ପଳେଇ ଆସିଲା ଆମର ତ ଆଜି ରାତିରେ ଆପଣଙ୍କର ପଇସା ମତେ ଡାକିବେ ମୁଁ ପଳେଇ ଆସିବି ଠିକ ଠିକ ସେଟା କରିଦବା ମୁଁ ତାକୁ ନେଇକି ମାର୍କେଟ ଯିବି ହଁ ଠିକ ଅଛି okay so Hamiltonian you can calculate from using this formula again this quantity we can found it is a total energy by using not necessary I have written here what is actually what that quantity tells we know L is equal to T minus V that's true but what is H for that we have to calculate this summed over J Pj Qj dot Pj is we know del L by del Qj that true or which is del T by del Qj dot what is a kinetic energy but we know that if constant is time independent then energy is conserved time independent constant means Clairaut-Amorth constant. So Lagrangian does not contain time explicitly, and so kinetic energy can be expressed as a homogeneous quadratic function of generalized velocity. If it is time, you can express T as a homogeneous quadratic function of generalized velocity. From Euler's theorem of mathematics, we know that if f is a homogeneous function of order n, then of a set of variable xi, then summed over z del f by del I xi is equal to nf. The Euler identity, integration in plus mathematics book. So I can use that. If you use that formula here in place of f, we have del f by del x into xi. Okay. Here pj is del t by del qj dot. F is our t. Xi is qj dot. Here qj dot. So f is t. T is a homogeneous quadratic means n order 2. So 2f. So f means t. So we found summed of pj qj dot is nothing but 2 into t. T is kinetic energy. Okay? Using this theorem only. So if I put 2t here, so h is equal to 2t minus L. 2t minus L. 2t minus t minus v. So what is that? 2t minus t, t plus v. So Hamiltonian is equal to total energy. For a conservative system, T plus V is total energy, kinetic potential energy, total energy. Okay, that's the proof. So for Hamiltonian is equal to total energy. Okay? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Oh. Next we go for Hamiltonian. Oh. So we know Hamiltonian is formula is summed of Pj Qj dot minus L. So as L is a function of Qj dot T, but Hamiltonian is a function of Qj Pj T. So when we find Hamiltonian for Lagrangian, you have to must replace all Qj dot through Pj. If you write H in terms of Qj dot, then it will be wrong. Okay, you have to write H in terms of Qj Pj T. Okay, so all Qj dots must be replaced by Qj or Pj and T during Hamiltonian. Okay. If you take its derivative dH, then equal to formula like Lagrangian last case, you can write del h by del Qj into dQj, del h by del Pj dPj, plus del h by del T into dt. Again, formula H is equal to Pj Qj dot minus L. So taking its dH, it will be summed over Z dPj Qj dot plus Pj dQj dot. Okay, for L, we have already derived this. Right there, and then but Pj is equal to del L by Qj dot. use here del L by del Pj is equal to del L by del Qj dot. We have Pj here. So these term cancel. A plus minus cancel. So we have only three terms. Here we have three terms. And compare the coefficient. Left hand side is same. So write a dqj. What is multiplied with dqj? And like this. With dpj. Multiply thing is this. Clear? So comparing the coefficient of dpj, you can say qj dot is equal to del h by del pj. Similarly, del L by del Qj is equal to Pj dot. We got in the last expression. Last slide. Pj dot is equal to del H by del Qj. Again, del H by del T is equal to del L by del T. These three are known as Hamilton equation of motion. By comparing this, we got that relations. Okay. Lagrange's equation, you can find Pj dot del L by del Qj. Because in this equation, if you put this is equal to del L by del Qj is equal to dpj by dt. Now dpj by dt means pj dot. Pj dot is equal to del L by del Qj. Okay, comparing the coefficient of equation 1 and 2, we found these relations. Qj dot is equal to del H by del Pj, Pj dot is del H by del Qj, and del H by del T is equal to minus del L by del T. This is known as canonical equation of Hamilton equations. And there are actually two F number. F number of J varies from 1 to F. So there are F equations. Here F equations. F plus F, 2 F equations. It is one equation, but these two are known as Hamilton's canonical equation. And its details we will discuss in the our second classical mechanics part 2. Okay. So these are the canonical formula. So for a cyclic coordinate, you can see cyclic coordinates also does not appear in the Hamiltonian. Cyclic coordinates mean del L by del Q is 0. So the del L by del Q is 0. Hello? Pj
Yes, sir.
constant. But Pj dot is equal to minus del H by del Qj. So Pj constant means Pj dot is equal to 0. So del H by del Qj is 0. If a coordinate is cyclic, means does not appear in the Lagrangian, then it also does not appear in the Hamiltonian. A cyclic coordinate does not appear in the Hamiltonian. Okay, it is proof for that. Next, there are some problems. Actually, the dynamics of a particle is governed by the Lagrangian. A Lagrangian is given according to the nature of the motion. And nature means we have to find the equation of motion first by using Lagrange's equation of motion. This is the Lagrange's equation of motion. So L is given. So taking derivative, you got this derivative of this minus this, and comparing, you find mx dot is equal to 0. Mx dot 0 means mass into acceleration force. Force is 0. Force 0 means motion of a free particle. When there is no force, the motion is called free motion. A motion of a free particle where potential force is 0. Okay. Then second problem, the Lagrangian system is given. Find the conserved momentum. You see, conserved momentum means the corresponding coordinate is cyclic. Here you see theta is present, but phi is not present. Phi not present. Theta not present, but phi is absent. So phi is a cyclic coordinate. If phi is cyclic, corresponding momentum is conserved quantity p phi, and p phi is a formula del L by del phi dot. Using that, I found this is a constant quantity. Okay. Hello.
Yes, sir. Yes, sir.
And problem. The Lagrangian of a system is governed by this. Find the cyclic coordinate. X square plus y square plus half z square. Actually, here option is given spherical polar coordinate. In fact, we have to convert this. You will know the formula in mathematical physics. In spherical coordinate, we convert from Cartesian. X is r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta. Putting those things, we found Lagrangian is this. So which one is cyclic? Theta present, phi present. If you take common r square sin square theta, then it will be cos square phi plus sin square phi. Cos square phi plus sin square phi is 1. So this will be removed here. So it is only r square sin square theta plus r square half r square cos square theta. So phi is a cyclic coordinate. Okay?
Yes, sir.
There are some problems on Lagrange's equation. think that's some rules. So when we calculate the potential, uh, potential energy characteristics of the system and not of any of the individual object within the system. Positive gravitational potential energy means that body will do work in returning to its reference position. While negative potential energy means work will be done on the body. When we sign, take in case of simple pendulum positive, Arthur's machine negative. Okay. Actually, positive negative can be decided for a gravitational potential if it work done by the system and positive work done on the system to negative. Or other way you can say depending on the reference point. If the reference point is above, then we call negative. Is below, then we call a positive potential energy. Okay. And there are some problems. A particular mass m slides under the gravity without friction along the parabolic path y is equal to x square. As shown in the figure, here a is a constant and find the Lagrangian. So I have calculated the parabolic path y is equal to x square given, but we know a two-dimensional motion kinetic energy is half m x dot square plus y dot square. So y is equal to x square. So dy by dt or y dot is equal to 2ax x dot. Putting here, we
Sir,
found half the kinetic. Huh?
sir, does this type
Hello?
of numerical question comes in exam?
Yes, it may come. I don't know exactly. Uh,
Okay, sir.
okay. Uh, so kinetic energy, if you put y dot square, you get like this. And potential energy. Potential energy are mgy. Mgy. Y is okay. When it's falling down, body again in moving here, it is really negative. Uh, work done on the system to move here, so it is not falling actually due to its own. So potential is negative and minus mgy, y plus we write ax square. So find the Lagrangian, then using that we get the equation of motion. Another problem, if the Lagrangian of a particular mass A moving in one dimension is given by this, where b is a positive constant, find the coordinate of the particle. How you find the coordinate? Then you go for equation of motion, then you find the coordinate. Equation of motion of this, the equation of motion contains acceleration, x double dot. Okay, so equation of motion d by dt mx dot plus b is equal to 0. Lagrangian is given. Use this del L by del x is equal to minus b minus minus plus del L by del x dot is equal to mx dot. Okay, so it will be mx double dot plus b is equal to 0. X dot double dot minus b by m. So how you get x? Double dot integrate it. First integrating it, I write x dot is equal to minus bm by t plus c1. Again, second integrating it, we got the, sorry, second get integrating this, we got the x is equal to minus b by 2 mt square plus c1 t plus c2. Okay. Another problem, a particle of unit mass moves in the xy plane in such a way that x dot t is equal to yt and y dot t is equal to minus xt. If it is a conservative force field, then find the potential from which the force is derived. Even x double dot is equal to y dot. If x dot is equal to yt, x double dot y dot minus xt, y double dot minus x dot. Okay, so d by dt del L by del x dot minus del L by del x 0. D by dt del L by del L y dot minus del L by 0. The Lagrange equation for x and y. So x double dot is equal to minus x. If you add this, x double dot plus x is equal to 0. Similarly, y double dot plus y is equal to 0. Okay. Now from this integrating, you can find x and y or comparing potential energy. I found this. The potential energy is a function of half x square plus y square. So Lagrangian t minus b. So we got this potential energy. Let's find the equation of motion of a system described as the time dependent Lagrangian. Lagrangian is given. You have to find the equation of motion. The equation of motion simply take del by del x and del by del x dot and use this. Okay, I'm not going to detail. A particle is moving under the action of a generalized potential. Calculate the generalized force. we have equation F2. Ah,
Sir, can I got this problems in PDF form?
yes, I share this in your group.
Yes,
Okay,
sir will send in the group.
there you go. So for generalized potential, the formula to getting the generalized force, we're using this formula d by dt of del v by del q dot minus del v by del q. Using this, we found this. Again, another problem. Okay, so that it's not necessary. Okay, okay, this is all about Lagrange and Hamiltonian. Then we go for next actually conservation things. See, okay. It's actually written a conservation of linear momentum and angular momentum. Okay, written here in part 1. Actually, there is a basic theorem called Noether's theorem. Noether's theorem statement is every symmetry of a nature yields a conservation law. Every symmetry of nature yields a conservation law. So conversely, every conservation law reveals an underlying symmetry. So symmetry and conservation they are associated. There is a famous theorem called Noether's theorem. Basing on that, we can say if symmetry is translation in space, then linear momentum is conserved. If the motion is unaffected by the change in space, then we call linear momentum is conserved. If it is motion is not affected by the change in time, then we call energy is conserved. So if the motion is not affected by the rotation, then we call angular momentum is conserved. Then another reading of dynamics is gas transformation and charge is a conserved quantity. Okay, these are the property and the conservation law. Conservation of linear momentum. Okay. Uh, so by we can prove this, which is also written in our syllabus, conservation of linear momentum. For that, we consider a system with ith particle whose position coordinate riqj. There is a change dri, change due to the motion dri, dqj. Since it is a vector, it is a direction n cap. It is riqj. Next, we got the change ri prime due to dri. Okay. So this dri change is nothing but change in the coordinate qj into a direction n cap. So from the Lagrange's equation, we know this d by dt del L by del qj dot minus del L by del qj is equal to 0. Or where we found pj is equal to del t by del qj dot. But del L by del qj dot, which is actually basically del t by del qj dot, is what? If you see del t by del qj dot minus del v by del qj. Del t by here we take derivative with respect to qj dot and find pj. By taking derivative with respect to qj, we found generally t kinetic energy contain velocity, so it is not contain coordinate. The derivative is 0. Only potential energy contain qj, so it is minus del v by del qj, which is our generalized force. We have already written there generalized force. So from comparing these two, we can say since these two are same from Lagrange equation, qj qj is same as it is what del L by del qj dot means this quantity is pj. So dpj by dt is same as del L by del qj, or del L by del qj is equal to capital Qj. So dpj by dt is same as capital Qj, or you can say pj dot is equal to qj. Now we have to prove this pj dot and qj how it is related with translational motion. Okay, what is qj? Qj is generalized force. Generalized force by definition it is Fi dot del Ri by del qj. Here dri is equal to del qj n cap. So del Ri by del qj is nothing but n cap only. So I write n cap, so it will be qj f dot n cap means component of force along the direction of change or translation. Similarly, pj, if you see pj is equal to del t by del qj dot, t is equal to half mv square or half mi ri dot square, and in that I find mi ri dot del ri by del qj. Again, del Ri dot by del Qj dot by cancelling dot, it is del Ri by del Qj, which is n cap. So it is nothing MIRI dot MV momentum P. So P dot n cap. That means Pj is nothing but a component of linear momentum along the direction of translation. So we found Pj dot is equal to Qj. So if Qj is 0, Pj is constant. So if force is 0, linear momentum is constant. That quantity, that is our conservation of linear momentum. Okay. So if Qj is cyclic coordinate, then it will not appear Lagrangian. Thus, the system is not affected by the translation of dQj, and hence linear momentum is a conserved quantity. Similarly, for conservation of angular momentum, you can prove taking the angle. Here change will be actually initially Ri, it goes to dRi. This change is related to rotation, a rotation around this axis along the NQ unit vector n cap due to this rotation change. So that you can write the changes Ri sin theta dQj. Okay, this change Ri since the angle is theta, Ri sin theta and dQj, which you can write n cap cross Ri dQj is the change. We proceed previous way, but the dRi n cap cross Ri dQj. So del Ri by del Qj is n cap cross Ri. Okay, you can prove Qj is equal to n cap dot tau, and Pj is nothing but n cap dot angular momentum L. So comparing this, you can say torque is 0, angular momentum is a conserved quantity. It's same, the repetition of that. Okay. Conservation of energy, we have already discussed. These are the things that is written in our syllabus. Okay. This is all about the Noether's theorem. Hello? Any problem?
Sir, syllabus subject.
A syllabus link you can find it from IGNOU side. Actually. They give the link where syllabus is given, different unit.
Okay.
Then, okay, this is another thing in our syllabus, Hamilton's principle. Okay. This is all written, Hamilton's principle. Actually, Hamilton's principle is applicable to monogenic system. All monogenic system, for all monogenic system, we apply this theorem. All monogenic system is the mechanical system for which all forces except the force of constant are derivable from a generalized scalar potential. We know conservative is a subset of monogenic. For a conservative, uh, force is negative gradient of potential, force is derived from potential, and potential is a function of coordinate only. But for a monogenic, potential may contain velocities, but force is negative gradient of potential. If force is only negative gradient of potential or derivable from a potential, we call it a monogenic system. If force potential function of coordinate only, then we call it conservative. So conservative is a subset of monogenic system, and our Hamilton's principle is applicable to all monogenic system. For monogenic systems, Hamilton's principle can be stated as the motion of the system from time t1 to t2 is such that the line integral LDT has a stationary value for the actual path of motion. Uh, Actually, here time is variable. System is moving with respect to time. Okay, from 1 to 2. For actual path of motion, it is also known as least action principle. Uh, this value L dt or this integral has a stationary value, generally minimum. For the actual path, there are many paths possible between 1, 2, this is another path, this is another path. But for actual path of motion, this integral, which is called as action, least action principle, this quantity I is known as action. Okay, least action principle, action is minimum. action integral or action. This quantity known as. Okay, you can use some techniques to prove this. Let's say consider a general case. Actual we got L is a function of Qz dot t and time is variable. Let's in place of L we have a function J which is on y dot x. Y dot means dy by dx. Here we assume and x is variable not t. There we compare with t. Then this is the actual path J dx. Okay. For one dimensional problem, let's consider y dot t define a path yx where y dot is equal to dy by dx. Our integral is j function of y dot x. For actual path of motion, the j should be extreme, maximum, minimum, stationary. Okay. So if j is stationary, then variation will be 0, delta j is equal to 0. How we solve this problem? Let us consider a nearby path. Suppose it is actual path. We consider a nearby path which is slightly different from actual path. Actual path means it path through 1 and 2. All path passes through 1 and 2. So if we take any path nearby it, then it vanishes 1 and 2, they match. So if I take that new path will be yx alpha, yx0 is the actual path, yx0 plus alpha eta x, so that eta x vanishes at x is equal to x1 endpoints and x is equal to x2. So this vanishes means two paths same because the endpoint is same. Okay. Now put this as take its yx alpha as a function here and take the differentiation and compare delta j is equal to 0 for actual path, putting alpha is equal to 0 because for actual path alpha is equal to 0. Actual path is yx0. So you put alpha 0 this is actual path. And putting the condition, actually we get this integral derivative f by y dot dx to taking its integration. So the integration by parts, we get like this dj by dx is simply integration, and using del f by del y we found an equation y dot del y by del x integration del f by del y dot by del alpha, putting, and at endpoints it vanishes. Considering that, we got actual final expression del j by del alpha is equal to this. The alpha, since alpha is an arbitrary thing and integration over dx, we can say this bracketed term, this one must be 0 since it, and because the delta j is minimum, maximum or stationary, so delta j is equal to 0. So it is basically delta j is equal to this is delta alpha. Okay. So this is the equation. If this is 0, bracketed term must be 0, which is actually basically our, if f is equal to L, y is equal to qj, x is equal to t, then the Lagrange's equation. But this general expression is known as Euler-Lagrange's equation. Derivation of Euler. Exactly by putting f is equal to Lagrangian L, y is equal to qj, x is equal to t, we got this equation, Lagrange's equation from Hamilton's principle. Okay, with derivation of Lagrange's equation from Hamilton's principle, the same thing procedure. Actually, we here put f is that was written in same way. You can understand it. I'm not repeating that. Putting only this L, f is equal to L, j is equal to I, qj is equal to y, x is equal to t. Putting that, we get the Lagrange's equation. If question like derive the Lagrange equation motion from Hamilton's principle, you first derive like this and then put these quantities. Okay. Hello? You can check it. All are written here. All steps are done here. You only verify. Okay?
Yes, sir.
Yes, sir.
Okay, you can do by yourself. All are given here. Then this is your derivation of Lagrange's equation. Another some problems are find the shortest distance in a plane. The shortest distance between 2 points, 1 and 2. How you calculate? You first consider a small arc length of this curve. Let a small arc length ds, but since it's a two-dimension ds, it look like this. So it has x coordinate and y coordinate. So that small length must be equal to dx square plus dy square root over. I can simply, if taking dx outside, I can write 1 plus dy by dx square, dy by dx y dot, 1 plus y dot square root over dx. So what is the total length? Integrating it from 1 to 2, 1 y dot square dx. But we know that shortest minimum, this integral should be minimum if it obeys Lagrange's equation. This function obeys Lagrange's equation. We know if y dot is have a stationary value or minimum value if dy by dx del f by del y dot minus del f by del y 0. So in place of f, write 1 root over 1 plus y dot square. Here f is root over 1 plus y dot square. Putting this, we found del f by del y 0, del f by del y dot is equal to this. Using equation 0, so this will be 0. This term is a constant, and again y dot here, integrating that, we found y dot square is this. So y is equal to ax plus b. It is the equation of a straight line. So the shortest path is a straight line in a plane, is a straight line. Okay. Another problem is minimum surface of revolution. By revolving a curve, we get many surface. For which surface? The surface area is minimum. That is our aim. We revolve this curve around this y-axis. Okay. So for that, we have considered a simple strip. Instead of rotating whole curve, let us consider a small ds. ds will rotate around y-axis. It will give this curve, small curve. What is the area of that curve? That is actually, if it is x, this quantity, x-axis, so x. So it is area 2 pi x, its perimeter 2 pi x, and then for small width ds. So area of the dotted region 2 pi x ds. For total surface, it will be integrated. 2 pi ds means the area dx square plus dy square root over. We know that. So this will be 2 pi x dx square plus dy square root over. Using that, we found 2 y dot is equal to dy by dx. We found this 2 pi x 1 plus y dot square dx. And this is our f now. But it should be minimum dy by dx del f by del y dot minus del f by del y 0. Putting in place of f and taking derivative, all things calculate, we got this one. Just simplifying. Simplifying, we got this surface of revolution is like this, which is a catenary. Another problem, Rachistogram, it's not required here. Long problem. Okay. This is all problems related to Hamilton's principle. Okay, hand out.
No, sir.
All are written here. You have to study it and write one
Sir.
to calculate one.
Sir, could you provide some important question related to exam so that we can prepare those questions?
Actually, I don't know the exam pattern. What type of question they will ask?
Some long question or short question? Because
Okay.
we don't know anything. What type of question comes, we know the mark schemes, but any type of question so that we can prepare.
Okay. I'll see. I'll send you. Okay, in the next class.
Yes, sir. Yes, sir. Next class.
Okay. Actually, in the first part of classical mechanics, we have two sections. One section is completed. The second section is central force motion. We'll discuss in the next class. Perhaps tomorrow, if South sir will take both classes, I think, because I have a work. And Friday, I will take your class on central force motion. Okay. So one part is covered of your classical mechanics one section Lagrangian and Hamiltonian, that is actually completed. And second part is central force motion. I will discuss in the next class. Okay.
Okay, sir.
Yes, sir.
Okay, sir.
Okay. Thank you. Yeah, I'll
So
send
kindly
this.
share this PDFs in the group.
I'll send.